This is the video for Part 2 of Chapter 15, Geometric Constructions. The key to the impossibility proofs is to translate the geometric problem to an algebraic problem. As we'll see, constructions with a straight edge correspond to solving linear equations, while constructions with a compass correspond to solving quadratic equations. We'll make this connection explicit in the following three lemmas. The first is lemma 15.3. Let f be a subfield of the field R of real numbers. And then first, if a line contains 2 points whose coordinates are in f, then the line has an equation of the form ax plus by plus c equals 0 for some a, b, and c in f. So this is saying that the coefficients of the line belong to f. Second, if the center of a circle is a point whose coordinates are in f, and the radius of the circle is a number whose square is in f, then the circle has an equation of the form x squared plus y squared plus rx plus sy plus t equals 0 for some r, s, and t in f. So again, the coefficients of the equation of the circle belong to f. We'll start the proof by proving 1. So we have a line containing 2 points whose coordinates are in f. So let's suppose that x1, y1 and x2, y2 are points on the line with x1, y1, x2, y2 all belonging to f. Now in the case that x1 equals x2, then the line is vertical and the line has equation x equal x1, which can be written in the form 1 times x plus 0 times y minus x1 equals 0, which has coefficients in f. So the result holds. Now in the case that x1 is not equal to x2, then the line has slope m equal y2 minus y1 over x2 minus x1, and the equation, using the point slope formula, will be y minus y1 equals m times the quantity x minus x1. And the equation can be written in the form m times x minus y plus the quantity y1 minus m times x1 equals 0. And since f is a field and the coordinates x1, y1, x2, y2 all belong to f, then the slope m also belongs to f, and the coefficients of the equation are in f. And so this proves part 1 of the lemma. For part 2, we want to look at a circle whose center has coordinates in f and whose radius squared belongs to f. So let's suppose the circle has center hk and radius r with h, k, and r squared all belonging to f. The circle then has equation using the standard formula for the equation of a circle of x minus h quantity squared plus y minus k quantity squared equal r squared. And expanding out the two quadratic terms, we get x squared minus 2hx plus h squared plus y squared minus 2ky plus k squared equals r squared. And this can be written in the form x squared plus y squared plus minus 2h times x plus minus 2k times y plus h squared plus k squared minus r squared equal to 0. And since f is a field and h, k, and r squared all belong to f, then the coefficients of the equation are in f. And this proves part 2 of the lemma. Now we'll call a point P equal x naught, y naught, whose coordinates are in a field f an f point. We'll call a line ax plus by plus c equals 0, and a circle x squared plus y squared plus rx plus sy plus t equals 0 with coefficients in f, an f line, and an f circle, respectively. The lemma tells us that a line passing through two f points is an f line, and a circle whose center is an f point and whose radius squared is an f circle. Now starting with f points, how can we construct new points? Well, there are 3 possible ways using a straight edge and compass. First, we can take the intersection of two f lines. Second, we can look at the intersection of an f line and an f circle. And third, we can look at the intersection of two f circles. We want to determine the type of points each construction generates. So we'll start with the intersection of two f lines. So let's suppose that L1 and L2 are two f lines with equations shown. So a1x plus b1y equals c1 and a2x plus b2y equals c2 with coefficients in f. And let's suppose that L1 intersects L2. We can use Cramer's rule or elimination to find the intersection point. So using Cramer's rule, the intersection point will have coordinates. X will be the determinant of C1, B1, C2, B2 over the determinant of A1, B1, A2, B2. And this is B2, C1 minus B1, C2 divided by A1, B2 minus A2, B1. And the y-coordinate will be the determinant of A1, C1, A2, C2 over the determinant of the coefficient matrix A1, B1, A2, B2, which is equal to A1, C2 minus A2, C1 over A1, B2 minus A2, B1. Now, since F is a field and each AI, BI, and CI belong to F, then the intersection point XY has coordinates in F. So this shows that the intersection of two F lines is going to be an F point. Next, we want to look at the intersection of an F line and an F circle. So let's suppose that L1 is an F line and C1 is an F circle with equations shown with coefficients in F. And let's suppose that L1 intersects C1. Now, at least one of A1 and B1 is non-zero, since L1 is the equation of a line. So let's assume that B1 is not equal to 0. Solving L1's equation for y, we obtain y is equal to 1 over B1 times the quantity minus A1x plus C1. And substituting this into C1's equation, we obtain x squared plus y squared will be 1 over B1 squared times the quantity minus A1x plus C1 squared plus R1x plus S1 times y, which is 1 over B1 times the quantity minus A1x plus C1 plus T1 is equal to 0. Now, after simplifying, we can see that this will result in a quadratic equation for x of the form ax squared plus bx plus c equals 0, where the coefficients a, b, and c will all belong to f. Using the quadratic formula to solve this equation, we obtain solutions x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And breaking apart the fraction, this will be minus b over 2a plus or minus 1 over 2a times the square root of b squared minus 4ac. And this can be written in the form x is equal to capital A plus capital B times the square root of k, where capital A is that first term, minus b over 2a, capital B is 1 over 2a, the coefficient of the square root, and k is the quantity under the square root, b squared minus 4ac. And each of these will be an element of f. Now, since we're assuming that L1 and C1 intersect, then the system has a solution, which means that k has to be greater than or equal to 0, the discriminant. Now, substituting the formula for x into the expression for y, we obtain y was 1 over b1 times the quantity minus a1x plus c1, and this will be minus a1 over b1x plus c1 over b1. And then substituting our expression for x, we obtain minus a1 over b1 times capital A plus or minus capital B square root of k plus c1 over b1. And this will be c1 minus a1 capital A over b1 plus or minus a1 capital B over b1 square root of k. And this shows that both coordinates of the intersection point will have the form p plus q times square root of k, where p, q, and k all belong to the field f. Now note that in the case that k is equal to 0, both coordinates will actually belong to f. Third, we want to look at the intersection of two f circles. And so let's suppose that C1 and C2 are two f circles with equations shown with coefficients in f. And let's suppose that C1 intersects C2. Now, the coordinates of the intersection points must satisfy both equations, so must satisfy the equation obtained by subtracting the second equation from the first, and subtracting the second equation from the first, the quadratic terms will cancel, and we'll be left with r1 minus r2 times x plus s1 minus s2 times y plus t1 minus t2 equals 0. And this is the equation of a line with coefficients in f, so is an f line. And therefore, the intersection points will be the intersection points of an f line and an f circle, so either C1 or C2, which we determined above to have coordinates of the form p plus q times square root of k, where p, q, and k all belong to f. So next, lemma 15.4 states, let f be a subfield of R and let k be a positive element of f such that the square root of k does not belong to f. And let's let f square root of k is the set of elements of the form a plus b square root of k, where a and b belong to f. Then two results. First, f square root of k is a subfield of R that contains f. And second, every element of f square root of k can be written uniquely in the form a plus b square root of k, with a and b belonging to f. Well, the proof of 1 will be a homework exercise. And to show f square root of k is a subfield, we can first verify that it's closed under subtraction and closed under multiplication to show it's a subring, and then show that it also satisfies axioms R9, R10, and R12. And this will imply that it's a subfield. So second, we need to show that every element of f square root of k can be written uniquely in the form a plus b square root of k, with a and b belonging to f. So suppose R is an arbitrary element of f square root of k, and let's suppose that R can be written as a plus b square root of k, and can also be written as the form as a1 plus b1 square root of k, with a, b, a1, and b1 all belonging to f. So we need to show that a1 is equal to a and b1 is equal to b. So we'll use a proof by contradiction, and let's just start by supposing that b1 is not equal to b. Now, since a plus b square root of k equals a1 plus b1 square root of k, that should be a k, not a k1, then a minus a1 will be equal to b1 minus b times square root of k. And since b1 is not equal to b, then b1 minus b is not equal to 0. So we can solve for square root of k, and we obtain a minus a1 over b1 minus b. And this implies that square root of k belongs to f, which is a contradiction. In our lemma, we suppose that square root of k did not belong to f. And so therefore b1 is equal to b, and hence a minus a1, which is equal to b1 minus b times square root of k, is equal to 0. So a is equal to a1. And so thus each element of f square root of k can be written uniquely in the form a plus b square root of k, with a and b in f. And this proves 2. Now the field f square root of k in the lemma is called a quadratic extension field of f. So we're essentially attaching the square root of k to the elements in f. Now from the discussion preceding the lemma, the intersection points of an f line and an f circle, or of two f circles, are either f points or f square root of k points for some k in f. The following lemma summarizes these results. So this is lemma 15.5. Let f be a subfield of R, and let L1 and L2 be lines whose equations have coefficients in f, so these are f lines, and let C1 and C2 be circles whose equations have coefficients in f, and so these are f circles. So then, first, if L1 intersects L2, then the point of intersection has coordinates in f. Second, if C1 intersects C2, then the points of intersection have coordinates in f, or in some quadratic extension field, f square root of k. Third, if L1 intersects C1, then the points of intersection have coordinates in f, or in some quadratic extension field, f square root of k. In summary, the intersection of f lines and f circles will be f points or f square root of k points for some k in f. We can now state a characterization of constructible numbers. And so this is theorem 15.6. For all real numbers R, if R is constructible, then there exists a finite chain of fields starting with Q, which we can call f sub 0, is contained in f sub 1, contained in f sub 2, all the way down to contained in f sub n, which is contained in R, such that R belongs to f sub n, our last field in the chain, and each f sub I is a quadratic extension of the preceding field. That is, f1 is equal to q of square root of c0, f2 will be f1 square root of c1, and so on all the way down to f sub n will be f sub n minus 1 square root of c sub n minus 1. For some c sub I and f sub I such that square root of c sub I does not belong to f sub I for each I equals 0, 1, 2, 3, up through n minus 1. A finite chain of fields, as in the theorem, is called a quadratic extension chain. So to prove this, we'll start by supposing R is an arbitrary constructible number. We need to show there exists a quadratic extension chain, as in the theorem statement. And since R is constructible, then starting with the points O, the origin, 0, 0, and the point P, equal 1, 0, the point R0 can be constructed by a finite sequence of operations of the following types. We can draw the line determined by A and B, where A and B are previously constructed points or elements of the set containing the origin and the point P. We can draw the circle with center A and radius the distance from B to C, where A, B, and C are previously constructed points or elements of the set OP. And we can determine the points of intersection of lines and circles formed using the operations in 1 and 2. So since R is constructible, we can construct the point R0, and the way we can construct the point R0 is starting with the points O and P. We can start by drawing lines or drawing circles, and then we can determine the points of intersections of our lines and circles. So we'll start with the two Q points, O and P. So these both have rational coordinates. And by lemma 15.3, the lines and circles determined by these points will be Q lines and Q circles. And by lemma 15.5, the intersections of these lines and circles will be either Q points or Q square root of C sub 0 points for some C sub 0 in Q. So let's let F1 be Q C sub, square root of C sub 0. By lemma 15.3 again, the lines and circles determined by points in F1 will have coefficients in F1, so they will be F1 lines or F1 circles, and by lemma 15.5 again, the intersections of these lines and circles will either be F1 points or F1 square root of C1 points for some C1 in F1. And we can let F sub 2 be F1 square root of C sub 1. Continuing, at the ith step, the lines and circles determined by the points in the previous step will have coefficients in a field f sub I, and the intersections of these lines and circles will either be f sub I points or f sub I square root of C sub I points for some C sub I in f sub I. And we'll let f sub I plus 1 be f sub I square root of C sub I. And since the point R0 is constructed by a finite sequence of operations as described above, then after a finite number of steps, we obtain a quadratic field extension f sub n equal f sub n minus 1 square root of C sub n minus 1 containing our point R0. So therefore there exists a quadratic extension chain Q equal f sub 0 contained in f sub 1 contained in f sub 2 all the way down to contained in f sub n as described in the theorem. And this completes the proof of the theorem. Next we need to discuss roots of polynomial associated with some of the results that we've proved in this chapter. So to show that the three construction problems are impossible, we need some preliminary lemmas. So the first is an analog of lemma 4.29, which show that for polynomials with real coefficients, the conjugate of complex roots is also a root. So lemma 4.29 said, for all polynomials f of x in R bracket x, so that means with real coefficients, and for all a plus bi in C, if a plus bi is a root of f of x, then a minus bi is also a root of f of x. So if you have a polynomial with real coefficients and you have a complex non-real root, then the conjugate of that root is also a root. So in this chapter, we're going to have lemma 15.7. So let f be a subfield of R, and f of x is a polynomial in f bracket x. So this has coefficients in f. And let's suppose that a, b, and k belong to f, but square root of k does not belong to f. And then if a plus b square root of k is a root of f of x, then a minus b square root of k is also a root of f of x. So essentially we're sort of saying if we have a root of the form a plus b square root of k, then its conjugate a minus b square root of k is also a root. So to prove this, we're going to first show that elements of f square root of k have several properties similar to those of complex numbers. So for any u equal a plus b square root of k in f square root of k, let's let u bar be a minus b square root of k. So we'll use the same notation as complex conjugates. Now it's straightforward to verify that for any elements u equal a plus b square root of k and v equal c plus d square root of k in f square root of k, then u plus v bar will be equal to u bar plus v bar, and uv bar will be equal to u bar times v bar. Also, u bar is equal to u if and only if b is equal to 0, which holds if and only if u belongs to the field f. So we can use these properties to prove the lemma. So let's suppose that f of x equal a sub n x to the n plus dot 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 down to a sub 2 x squared plus a1x plus a0. And let's suppose that u equal a plus b square root of k is a root of f of x. So we need to show that u bar equal a minus b square root of k is also a root of f of x. Now since u is a root of f of x, then f of u is equal to 0, where f of u will be a sub n u to the n plus down to a sub 2 u squared plus a1u plus a naught. And using the above properties, we obtain f of u bar is just the expression f of u with a bar over it. And this will be equal to a sub n u to the n bar plus dot 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 down to a sub 2 u squared bar plus a1 u bar plus a naught bar. So the bar over the sum is going to be the sum of bar over each of the individual terms in the sum. And this is going to be a sub n u to the n bar plus dot 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 down to a sub 2 u squared bar plus a1 bar u bar plus a naught bar. And since each of the coefficients in f belong to the field f, then when we put the bar over a sub n, it's just going to be the same as a sub n, and similarly for a sub 2, a sub 1, and a sub naught, all the coefficients. And so this ends up being f of u bar. And again, note that since f of x is in f bracket x, its coefficients belong to f, then a sub I bar is equal to a sub I for each I. And since f of u is equal to 0, then we obtain f of u bar is equal to f of u bar is 0 bar, which is just 0. So this shows that u bar is a root of f of x. And this proves the lemma. Next we have lemma 15.8. Let f be a subfield of a field k for all f of x, g of x in f bracket x and h of x in k bracket x. If f of x is equal to g of x times h of x, then h of x is actually in f bracket x. So f is contained in k, and f and g have coefficients in f, and h has coefficients in the larger subfield k. But f of x equals g of x times h of x implies that h of x actually has coefficients in f. So to prove this, let's suppose that f of x and g of x are arbitrary polynomials in f bracket x, and h of x is an arbitrary polynomial in k bracket x. And let's suppose our hypothesis f of x equals g of x times h of x. We need to show that h of x is in f bracket x. Now the hypothesis f of x equals g of x times h of x implies that g of x actually divides f of x in k bracket x. By the division algorithm in f bracket x, when dividing g of x into f of x, there exist quotient and remainder polynomials q of x and r of x in f bracket x, such that f of x equals g of x times q of x plus r of x, and r of x is either 0 or the degree of r of x is less than the degree of g of x. Now note that since f is a subfield of k, that should be a capital K, then q of x and r of x are also in k bracket x. And since the quotient and remainder in the division algorithm are unique, then q of x and r of x must be the quotient and remainder when applying the division algorithm in k bracket x also. However, according to the hypothesis in k bracket x, f of x equals g of x times h of x, and this is g of x times h of x plus 0. And this implies that the quotient and remainder when dividing g of x into f of x in k bracket x are actually h of x and 0, since this has the form of the result from the division algorithm. So it must then be the case that our quotient q of x is actually equal to h of x, and our remainder r of x is actually equal to 0. And since q of x was assumed to be in f bracket x, this tells us that h of x is in f bracket x, and this proves the lemma. We're now ready to prove our main theorem, which gives us a criteria for showing that a given number is not constructible. This is theorem 15.9. For all cubic polynomials f of x in q bracket x, if f of x has no roots in q, then f of x has no constructible numbers as roots, and hence any roots of f of x are not constructible. So to prove this, we'll use a proof by contradiction. So let's suppose that f of x is a cubic polynomial in q bracket x that has no roots in q, but f of x has a real root that is constructible. We then need to derive a contradiction. By theorem 15.6, for each constructible root of f of x, there exists a quadratic extension chain of q. Among all such quadratic extension chains containing a root of f of x, we can choose one that has the shortest length. So this will be q is equal to f naught contained in f1, contained in f2, all the way down to contained in f sub n. That is, f of x has a root r in f sub n, but no quadratic extension chain of length n minus 1 or less contains a root of f of x. Now, since r belongs to f sub n, but f of x has no rational roots, then f sub n can't be equal to q, because r is definitely not rational. Since r is a root of f of x in f sub n, then by the factor theorem, which is theorem 4.16, f of x is equal to x minus r times t of x for some t of x in f sub n of x, f sub n bracket x. Now, by the definition of a quadratic extension chain, f sub n is equal to f sub n minus 1 square root of k for some k in f sub n minus 1 with square root of k not contained in f sub n minus 1. Now, since r belongs to f sub n, then r must have the form a plus b square root of k for some a and b in f sub n minus 1. By lemma 15.7, since r equal a plus b square root of k is a root of f of x, then r bar equal a minus b square root of k is also a root of f of x. And by our assumption, the shorter chain, q equal f naught contained in f1, contained in f2, all the way down to f sub n minus 1, cannot contain any roots of f of x. We assume that our chain was already the shortest chain containing any roots of f of x, so if we take a shorter chain, it cannot contain any roots of f of x. So this implies that r cannot belong to f sub n minus 1, which implies that b is not equal to 0. Therefore, r is not equal to r bar, so r bar must also be a root of f of x in f sub n. So then by the factor theorem, f of x is equal to x minus r times x minus r bar times h of x for some h of x in f sub n bracket x. So let's let g of x be the product x minus r bar. So then g is equal to x minus a plus b square root of k times x minus a minus b square root of k. In multiplying these two factors together, we're going to get x squared minus 2ax plus the quantity a squared minus kb squared. And since a, b, and k all belong to f sub n minus 1, this tells us that g of x is in f sub n minus 1 bracket x. So then f of x equals g of x times h of x, where f of x and g of x belong to f sub n bracket x, but h of x belongs to f sub n bracket x. Lemma 15.7 then implies that h of x actually belongs to f sub n minus 1 bracket x. Now, since the degree of f of x is 3, it's a cubic polynomial, and the degree of g of x is 2, then the degree of h of x must be 1, which means that h of x is a linear polynomial. So h of x has the form cx plus d for some c and d in f sub n minus 1, where c is not equal to 0. So then s equal minus d over c is a root of h of x in f sub n minus 1. Now, since f of x equals g of x times h of x, then s must also be a root of f of x. So this contradicts the choice of the quadratic extension chain as having the shortest length among all chains containing a root of f of x, because we've now said that s is a root of f of x and s belongs to f sub n minus 1. So our contradiction completes the proof of the theorem. So now we're ready to discuss the impossibility proofs. To show that a geometrical construction is impossible, we want to use theorem 15.9 to show that a specific real number r is not constructible. To apply the theorem, we then need to show that r is a root of a cubic polynomial in q bracket x, so it has rational coefficients, that has no rational roots. More generally, it can be shown that a real number is constructible if and only if its minimal polynomial has degree equal to a power of 2. So a real number u is said to be algebraic provided that u is the root of some non-zero polynomial in q bracket x. It can be shown that if u is algebraic, then there is a unique monic irreducible polynomial in q bracket x that has u as a root. And this monic irreducible polynomial is called the minimal polynomial of u. In theorem 15.9, since the cubic polynomial f of x has no rational roots, then f of x will be irreducible in q bracket x. And by multiplying f of x by the reciprocal of its leading coefficient if necessary, we'll obtain a monic polynomial, which will be the minimal polynomial of r, which will also have degree 3. So since degree 3 is obviously not a power of 2, using the general result, it follows that, that r is not constructible. Okay, so we want to first prove that duplicating the cube is impossible with straight edge and compass. So we'll start with a unit cube with sides of length 1 and volume 1. Duplicating the cube then corresponds to constructing a cube with volume 2, which must then have sides of length cube root of 2. To prove duplicating the cube is impossible is then equivalent to showing that cube root of 2 is not a constructible number. Now note that cube root of 2 is a root of f of x equal x cubed minus 2, which has rational coefficients, so this is in q bracket x, and we claim that f of x has no rational roots. By the rational root test, if r over s is a rational root of f of x, then r must divide the constant term 2, and s must divide the leading coefficient 1. So the possible rational roots are going to be r over s equal plus or minus 1 and plus or minus 2. Now since f of minus 1 is equal to minus 3, f of 1 is minus 1, f of minus 2 is minus 10, and f of 2 is 6, then none of these are roots. So therefore f of x has no rational roots. So by theorem 15.9, f of x has no constructible numbers as roots, and since cube root of 2 is a root, then it must not be constructible. And so thus duplicating the cube is impossible. Next, we want to show that it's impossible to trisect an arbitrary angle by showing that a 60-degree angle cannot be trisected. Now note that some angles can be trisected by straight edge and compass. For instance, we can trisect a 45-degree angle. To show this, it suffices to show that we can construct a 15-degree angle, and since we can construct a 60-degree and equilateral triangle, then we can construct a 60-degree angle. By bisecting a 60-degree angle twice, we obtain a 15-degree angle. So to prove the theorem, we need a few preliminary results. The proof of the first is a homework exercise, and so this says that an angle of t degrees is constructible if and only if cosine of t is a constructible number. The second is a trigonometric identity. For any angle t, cosine of 3t is 4 cosine cubed t minus 3 cosine t. So this is a triple angle formula for cosine. And to prove this, we'll assume the cosine addition, the double angle identities for sine and cosine, and the Pythagorean identity. So cosine of 3t is equal to cosine of 2t plus t, and using the cosine addition formula, this will be cosine of 2t times cosine of t minus sine of 2t times sine of t. And then using the double angle identities for cosine and sine, this will be 2 times cosine squared t minus 1 times cosine of t minus 2 sine t cosine t times sine t. And multiplying this out, this will be 2 cosine cubed t minus cosine t minus 2 sine squared t cosine t. And then finally, using the Pythagorean identity for sine squared, this will be 2 cosine cubed t minus cosine t minus 2 times the quantity 1 minus cosine squared t cosine t. And then multiplying out terms and collecting like terms, we obtain the identity. This is 4 cosine cubed t minus 3 cosine t. So we want to use these results to prove our theorem that a 60-degree angle cannot be trisected with straight edge and compass. So in order to trisect a 60-degree angle, we need to construct a 20-degree angle. And by the first remark above, a 20-degree angle is constructible if and only if cosine of 20 degrees is a constructible number. So letting t equal 20 degrees in the triple angle identity above, we obtain cosine of 60 degrees is 4 times cosine cubed of 20 degrees minus 3 times cosine of 20 degrees. And cosine of 60 degrees is just 1/2. And multiplying this equation by 2 and collecting all terms on one side of the equal sign, we obtain 8 times cosine cubed of 20 degrees minus 6 times cosine of 20 degrees minus 1 equals 0. And this implies that cosine of 20 degrees is a root of the polynomial f of x equal 8x cubed minus 6x minus 1, which has rational coefficients. And we want to show that f of x has no rational roots. So by the rational root test, if r over s is a rational root of f of x, then r must divide 1, the leading coefficient, the constant term, and s must divide 8, which is the leading coefficient. And so the possible rational roots are plus or minus 1/8, plus or minus 1/4, plus or minus 1/2, and plus or minus 1. Okay, so it's straightforward to verify that none of these are roots. So I won't go through that. So therefore, f of x has no rational roots. And so by theorem 15.9, f of x has no constructible numbers as roots. And since cosine of 20 degrees is a root, then it must not be constructible, which implies a 20-degree angle is not constructible. And so thus a 60-degree angle cannot be trisected. So the last of the 3 classical construction problems is squaring the circle. Starting with a unit circle, can we construct a square with the same area? A unit circle has area pi, so to square the circle, we need to construct a square with sides of length square root of pi. To prove this is impossible, we need to show that square root of pi is not a constructible number. Now, we cannot use theorem 15.9 to prove this, since square root of pi is not a root of a cubic polynomial in q bracket x. In fact, square root of pi, indeed pi itself, is a transcendental number, meaning it is not the root of any polynomial in q bracket x. And this result was first proved in 1882 by Ferdinand von Lindemann. Now, assuming square root of pi is transcendental, however, we can conclude there does not exist a quadratic extension chain with square root of pi in f sub n. It then follows from theorem 15.6 that square root of pi is not constructible, and thus we cannot square the circle. So this finishes off our 3 classical construction problems. Each of them is impossible.